Welcome back to ECE 441A, 541A. I sent out an email, I believe, yesterday saying there was an extra lecture. It's about 20 minutes. It's designed to help you. We ran out of time in earlier class meetings, and I wanted to simply illustrate how you can use the Ruth array with an adjustable parameter to determine what the value of that parameter might be, or a range on that parameter for stability using the Ruth array. And that's lecture and or notes and video 5.3 in unit 5 on D2L. Homework 5 is due today. There are practice exams and a list of topics which you need to be aware of prior to Friday. Friday is exam number 2. Hopefully that surprises no one. And lab number 2 will be due a week after your exam number 2. Today, let's quickly cover the exam 2 process, which is consistent with what exam 1's process looked like. And we will actually get into some fun material. We will start motivating the root locus, and we'll try to explain what the root locus is, but it's essentially a locus of root locations. We want to know where are our closed loop poles in the complex S-plane, and the root locus provides us with a tool for determining where those closed loop poles will be located depending on a particular adjustable parameter. Exam number 2, what is allowed? Now you have 2 sheets of notes, front and back, 8.5 by 11. You can bring in a copy of table 2.3. I think that's available maybe on the exam 1 material section of D2L. If you don't still have that in your possession after exam 1, you can have a calculator and a writing instrument. What's not allowed, and at one point I just said not allowed textbook, and then I thought, they'll maybe just see, oh, textbook, class notes. No textbook, no class notes, no computer, no cell phone. That's the process for exam number 2. Today what I want to do is start getting into this new topic, which is the root locus, and that is a strategy or one way to think about designing controllers. If we're going somewhere new in terms of topics, maybe it's nice to connect that with what we already know so that we can progress maybe a little bit more smoothly or with a little bit more comfort. So if we're motivating the root locus, what have we learned so far? Or what are some of the things that we now know? We spent some time dealing with modeling. You've already spent, if you're an electrical and computer engineer, you spent a lot of time analyzing circuits or modeling circuits. If you are taking this class, we've now learned a little bit about mechanical modeling, and all of that allows us to create some G of S, a model of our system. Let's say, just for illustration purposes, which we will try to use throughout today, that we have a system that has this particular form. A numerator S plus 10 and a denominator of S plus 1 and an S plus 5. And what I want you to be instinctively doing is seeing that G of S in the S-plane. And how do you see that G of S in the S-plane? You now put X's and O's. So now you're playing a game. And you have X's and O's. The X's are your poles and the O's are your zeros. And you are now locating those, and those basically are starting. The poles, the X's, are where we start our root locus. And where are we going to begin our root locus journey for this particular system? In the S-plane. more than just the S-plane. Where in the S-plane will we begin our journey if we begin our journey on the poles? On the open loop poles. This is our open loop system, and we may not like the way our system is behaving, and so we want to change that or understand how it can be changed. Where are the poles of G of S? Where those factors go to 0 at S equal -1 and at S equal -5. This is a stable open loop system. It's an okay system. We do have a finite 0 at -10, but you should now see that pattern of poles and zeros in the S-plane mentally. What else have we done? We've done some work with design specifications. Meaning, if you are now given let's say the upper left section of a S-plane diagram, and I said something about settling time, what does that now invoke what mental image does that put on this S-plane if I say settling time? In terms of a design specification, what are you thinking? Settling time. Does that partition the S-plane in any way? And if it does, so that was 50-50. You could have flipped a coin, and half the time you would have gotten that answer right, yes or no. Yes is the answer. It does partition the S-plane. And how does it partition the S-plane? With what kind of a line? An angular line, a straight line, and is that straight line horizontal? Is it flat-lined, or is it up and vertical? It's vertical, isn't it? We now want to be to the left of some vertical line if we are actually concerned with some settling time specification. What if I give you a percent overshoot specification? Now what mental image do you impose on that S-plane plot? Now I say a percent overshoot, and I want less than, let's say, 20% overshoot. What do you see now? Now you see an angle, don't you? Or you see a wedge. You see a pie wedge or a pizza wedge. You now see this wedge shape, and it's now coming out from the origin. Here is our percent overshoot, and if it's a wedge, it actually has this reflection down in the lower half of the complex S-plane. But now, if you want less overshoot, which way does that wedge go? Does it shrink in size if you want less overshoot, or does it expand the angle? If you want less overshoot, you need to squeeze that angle, that wedge shape down if you want less overshoot. And if you wanted the intersection of settling time and percent overshoot, where would you be living? To the left of the vertical line and inside the wedge. Now, one more design specification we have already talked about, which is peak time. And that's this, another line. We now have 3 lines in our complex S-plane. This is now our peak time, or that's consistent with rise time. If we want a quicker responding system, we want to get to our peak more rapidly, sooner, which way does that horizontal line move? Towards the real line, towards the real horizontal line, a value of 0, or does it get taller? We want a faster responding system. All right, interaction. Thumbs up or thumbs down. If it goes up, I want your thumbs up. If it goes down, I want them down. And at the count of 3, I want you to give me a thumbs up or a thumbs down. This doesn't mean anything about the quality of the lecture, please, okay? This is just a thumbs up or a thumbs down. Which way does the horizontal line go if I want a smaller time to peak? Uncertain? That's allowed, I guess. You can now get both hands, but I was hoping you were still writing with one. It should be going up, right? If we want to reduce the peak time, meaning to make our system faster, we want to get there quicker, we need to have a faster system. So we need more omega sub d. We need to be higher up, further away from the horizontal line at 0. So those we've had. We have modeling, we have design specifications. Now if we wanted all 3, we wanted a certain percent overshoot, we wanted a quick peak time, and we wanted a reasonable settling time. Now do you see where we would be living? We would be in this region of the complex S-plane, the intersection of those. But I could, on the exam, we might as well talk a little bit about the exam since that's the next time we meet. I could phrase this to where you could be in all sorts of those regions, and I might have you shade a particular region. For example, I might say, I want your settling time to be greater than what's indicated by that vertical line. I want a peak time quicker than what's indicated by that horizontal line, and I want a percent overshoot less than what's indicated by the wedge. Where am I at now? I want a slower system, so now I'm to the left or to the right of that. I wanted a certain percent overshoot smaller than what's indicated, and I needed a quicker peak time. So now I'm in that little triangle. See how this is nice and colorful? You can now go home and color. You can get your 64 crayons out and be coloring these different regions. And then you can say something about each region relative to these design specifications. And we may want our desired closed-loop poles to be in there, in that spot. That's where we're headed, is where do we want to place these dominant closed-loop poles. We've also talked about the Ruth-Hurwitz, and how did we finish? Well, we actually finished before what I want you to answer now. Between last lecture and this lecture, what did you have available to you that you could think about in terms of this Ruth-Hurwitz? I gave you an email yesterday about something that was available to you dealing with the Ruth-Hurwitz, and what particular use or utilization of the Ruth-Hurwitz was that addressing? How could you phrase that? Stability depending on a variable parameter. So now we understand how to adjust a parameter, maybe a gain in our system, to either ensure stability or keep our system stable. So we know how to use the Ruth-Hurwitz to determine, let's say, a range of k for stability. We have a system through modeling. We know maybe what we want that closed loop system to be doing as far as its performance or as far as the specifications. We know that we can adjust a gain in our system to influence this relationship because we've done it once with the Ruth-Hurwitz. What if we wanted to put all of these together? That's what we want to do now. Maybe you don't want, but your boss needs, so I'll change that. what if we need all of this, or all of these pieces, to be put together or combined? Here's an example. Suppose somebody says, and maybe for it to be significant, maybe it's your boss. Your boss now says, I want a settling time less than 1 second. If your boss now, if she's now said, I want a settling time less than 1 second, what picture do you see? Do you see a mental image? And what plane are you in or on? You're in the complex S-plane in a particular location. You're probably stable, so you're in the left half S-plane. And settling time corresponds to some kind of a line, and you just told me it's this vertical line. So you should be expecting now, with a settling time, let's say a 2% settling time of 4 time constants, tau can be, or it's inversely proportional to the exponent in an exponential damping term. So that's the sigma. This is now, settling time is 4 over sigma, a 2% settling time, and you now want that to be less than 1 second. Well, that's a pretty easy algebra problem, isn't it? You now have 4 over sigma less than 1. You now know that you want sigma to exceed 4. You need to be far enough into the left half plane to be beyond a distance of 4 from the imaginary axis. So here's our S-plane. And suppose that we're playing with this system that we started with, S plus 10, S plus 1, S plus 5. And if we start marking this up, those are supposed to be uniform tick marks. Where can we now put our X's and O's in this complex S-plane for that particular system? Do I have any X's? The X's are poles, and I have 2 of those, and we just said where they were. -1 and -5. I now need to put an X at -1 and an X at -5. And I do have a circle. I do have a 0, and it's at -10. That's over here. And we'll figure out how that influences things as we go. But now, where is my vertical line for a sigma value bigger than 4? Now I need to have my dominant poles to the left of that vertical line. And you can see, maybe, it's pretty clear that that pole at S equal -1, which is an open loop pole, is not to the left. And which pole dominates? You have a -1 pole and a -5 pole. In a transient response, which pole dominates? The -1. That's the slowest pole. That corresponds to an e to the -t. The pole at -5 corresponds to an e to the -5t. E to the -1t is much slower than e to the -5t. This pole at -1 dominates your response. Let's just see that. Suppose somebody says, well, maybe I don't have to do much. Maybe I just apply a constant input to the open loop system, and I will satisfy my settling time spec. We sort of know that that's not going to be true based on our sketch just now. Here's our open loop system. We have our reference input, let's say R of S. Maybe somebody says, well, maybe we need a gain, so let's put a gain in there, a K. And then we have our system, S plus 10 over S plus 1, S plus 5. That's what our open loop system would look like. Open loop meaning we're not feeding any information back and comparing it in any way. We're just injecting an excitation signal, a reference input, and seeing what happens. We may adjust the gain K, and that will simply amplify our signals, but it's really not going to change the dynamics. How can we figure out what's going to happen? Suppose now somebody says, what's the system behavior of this system? They want to know, how is Y going to respond to an input R? Now what do you do? Let's not even worry about feedback right now. This is open loop. So now let's just give me the answer. Give me Y of t if I give you an R. How would you solve that problem? You just have to set up the algebra, don't you, from the block diagram. Block diagram algebra. It's just Y is K times the plant, G of S, times the input R. We now can find our system response in the frequency domain. Y of S is now K, G of S, R of S, where I'm now calling this, or have called that, G of S. Or this is now K times S plus 10 over S plus 1, S plus 5 times R of S. Now they have to tell you what R is, don't they? In order to you tell them what Y might be. If R of t, let's say little r of t is a constant, what does that tell you about R of S? That's a step, isn't it, of some magnitude. We maybe didn't say it's a unit step, but now it looks like A over S in the frequency domain. If this constant, let's say, was A for t greater than or equal to 0. That's our R of t. That now produces, in the frequency domain, in the Laplace case, A over S. Now, can you tell me structurally what Y of t is going to be? What's the structure of Y of t? Now, mentally put that R of S structure in for R of S, and now you have an expression for capital Y of S. And think back, think back, think back. A couple of semesters maybe. How do I find little y of t? Partial fraction expansion. All right, if we do a partial fraction expansion, what kind of pieces, what kind of fractions am I going to have? I'm going to have something over an s, something over a factor s plus 1, and something over an s plus 5 factor, and that will produce in the time domain some constant. That's due to the inverse Laplace transform of something over s, which in this case I'm saying it's alpha 1 over s. If somebody gives you the a and the k, you could find that. Then you have something due to the pole at minus 1 in the time domain, and you have something else due to the pole at minus 5, and this is true for t greater than or equal to 0, and you've done that just on the back of an envelope. Somebody gives you this g of s, and you now know the structure of y of t for a constant input to the system in the open loop. But you can hopefully see that y of t is not going to satisfy, in the open loop setting, our settling time specification. Y of t will not reach a settling time. It won't settle in a second. Y of t will not reach a settling time in 1 second. And you could do that if somebody says, well, why? How many time constants do you have? Where are you going to eventually end up in y of t? Where will you settle? Okay, we forgot that we had to put that subscript on something. It's alpha sub 1, isn't it? That's where we will settle because the exponents decay. We're going to eventually approach alpha sub 1. But how quickly do we approach alpha sub 1? There's two exponentials, meaning we have two time constants, don't we? We have a slow time constant and a fast time constant. What is our slow time constant? That's the 1 over sigma slow. Let's say that's 1 over 1, isn't it? This is 1 second. That's our slowest time constant. And we also we can see that we have a fast time constant, which is 1 over 5. That's what t in that third term will produce a 1 in the exponent. 5 times what gives us a 1? That's our time constant, and that's 1/5. This is our fastest time constant. And in this case, then, a 2% settling time will be influenced by our slowest time constant. 4 tau is dominated by that pole closest to the origin. So our 2% settling time of 4 tau sub s will be how long? 4. 4 times 1. And our boss wanted a 1 second settling time. We now, in the open loop, again, we're just talking open loop, we now have determined that we have something like that. And this particular point, when we're within 2% of where we eventually are going, and from our particular way of defining terms and values, we've now reached a settling time of 4 seconds, and our final value is alpha sub 1. Are we clear on that? Are we clear about dominant poles? This was pretty easy because they were sprinkled right on the real axis. If I now said, here is, maybe somebody gives you a fifth order system. Fifth order system means you have 5 x's, and these are all supposed to be mirror images since they're complex conjugates. Here is our S-plane for a fifth order system. Which of those poles dominate? Which poles will dominate our response? Closest to the imaginary axis, isn't it? The ones that have the smallest real part. And if they're pretty close, they're all going to sort of play together. But if these are separated a fair distance, maybe this real root is 5 times beyond the distance of the first poles, which it's not, but that's usually the separation that you need to say these are really our dominant poles. But in this class, we will just agree that we're going to focus on those two poles, if they're complex, as our dominant poles. These will be our dominant poles, and we will use our design specification information based on those two. If we have a fifth order system, we'll find the two that are closest to the, or have the smallest real part, and we'll say these are our dominant. Now let me figure my settling time, my percent overshoot, my peak time from those two poles. Is that clear? That's what we're meaning by dominant poles. Let's now, since the open loop didn't work, let's look at the closed loop scenario. We have our gain K, we have our system G. This is what we had before. Now what we want to do is we want to, that wasn't working for us. So now is it possible to maybe modify the system dynamics by introducing feedback? Can we now change the open loop to a closed loop, and hopefully now we will have better performance than what we had before? Because our boss wants a 1 second settling time, and the open loop system was giving us a 4 second settling time. What's the closed loop transfer function? Again, this you should just be able to almost do in your sleep, especially for exam 2. If I'm asking you sensitivity questions, I'm just assuming you can find the transfer function. You may have to ask, what's the transfer function between, or what's the input and the output, but hopefully it will be clear. Then you need to find that transfer function. What's the expression here? If you were looking for partial credit, you might do that. T of S, oh, it's Y over R. Give me some partial credit, please. But you can go further than that, right? What is it for this way in terms of just K and G? Kg over 1 plus Kg. It's kind of Kg, isn't it? Oh, that was pretty lame, but anyway. We have Kg over 1 plus Kg. We're okay on that, right? Now if we put all of this together, and a lot of times we are going to want just a ratio of a numerator polynomial over a denominator polynomial. If we parameterize our G as a numerator over a denominator, that's our open loop, numerator over denominator. We can now find K n of S over D of S all over D of S plus K n of S over D of S. We can get rid of the denominator and the numerator and the denominator, and we are left now with our closed loop transfer function in terms of zero factors and pole factors of our open loop system. Now looks like K times the numerator of our open loop system over the denominator of our open loop system plus K times the numerator of our open loop system. Our closed loop poles are some combination of open loop poles and zeros. And what that combination is depends on the gain K. So we can now change the closed loop poles and it will be related to our open loop poles and our open loop zeros, because that's the expression we just derived. Our closed loop poles are governed by the roots of d of s plus k n of s equal to 0. And we define this d of s and n of s. D of s corresponded to our open loop poles. Those were the poles of g of s. And the little n of s were the open loop zeros. And what we want to know now is we want to know how can we, or how do those closed loop poles behave as a function of this parameter or adjustable gain K. I always am doing this. I apologize for those of you that are home. You'll just have to come to class sometime and see my movement of this knob. K is a knob. It's an adjustable variable. We want to take that knob and move it from 0 up to infinity. And we want to ask, how do the closed loop poles behave as K moves from 0 to infinity? And that's our root locus. We are asking now the question, what happens to the closed loop poles as K is increased from K equals 0 to K marching all the way to a really big number towards infinity? And that is this concept called the root locus. We want to know what's the root locus. We want to be able to sketch that so that we can figure out, do those branches of the root locus pass through some of these desirable regions that we had from our design specifications? And if they do not, then maybe we need to put some more poles and zeros into our system by means of a controller. First, let's just figure out how to sketch a root locus as K is adjusted. Let's look at some cases. Suppose somebody says, well, what's going to happen if K is equal to 0? Now you basically don't have any feedback. Let's just consider it that way. Our expression was d of s plus k n of s equal to 0. With k equal to 0, how does that impact that expression? Now we're just going to have d of s equal to 0. And what are the values of s that satisfy that equation? What was d of s? -5 and -1 in our example. Those were our open loop poles, weren't they? So this is now when k is equal to 0, at the beginning of our root locus, our poles are the open loop poles. And those were at -1 and -5. What about if we let k be a little bigger? Suppose k is equal to 1/2. Then we have s plus 1, s plus 5. That was our d of s. Plus k, which now is 1/2, times n of s, which was s plus 10. And we want to know what values of S satisfy that. So how are our closed loop poles moving? We started at -1 and -5. Now we crank up the gain a little bit. Now we do have feedback. And we've cranked up the gain to a small value of 1/2. We can just push through the numbers. We now have S squared plus 6S plus 5. That's D of S multiplied down. Plus 1/2 S plus 5 equaling 0. Or that's now S squared plus 6.5S plus 10 equal to 0. And we have some ace algebra factors here in the audience. How are ways of combining two numbers to make 10, where those two numbers now add up to 6.5? It's not that bad, actually, once you see it. How about 4 and 2.5? That'll work, won't it? Ta-da! Okay, so now we have S is equal to -4 and S is equal to -2.5. Picturing what's going on. What if we go back to the S plane? Here was 1. I'm hoping I have the right number of tick marks. Here was -1 and there was -5. That was where we started. We now have closed the loop and injected or increased the gain to 1/2. And where did our closed loop poles, which I will now indicate by triangles, where did they move to? They're right there, didn't they? One went to 2.5. So now we go over here and we say, well, one of them is right there at 2.5, and the other one is at 4. We started with 2 poles. We still have 2 poles. We didn't increase, they didn't multiply or anything. We started with 2 open loop poles. We have 2 closed loop poles. And they now have migrated by adjusting the gain K. Are we doing better in terms of settling time than what we were? Now, where did we want to be? We wanted to be to the left of 4, didn't we? And we were quite a ways away with this pole at -1. Now it's slid over to -2.5, so it's getting better. This one now we sacrificed a little bit, but maybe we like the overall shape a little bit better. Which pole is dominating? The one that's at -2.5, but these two are so close together, they're sort of playing together, but we could just say, let's just assume that the slowest one is going to be what's dominating. The one at -4 will help that a little bit, so the -4 gives us a conservative estimate. I'm sorry, the -2.5 pole gives us a conservative estimate on our settling time. But that was good, wasn't it? By increasing the gain a little. What if we increase it a little bit more? Suppose we say, well, let's just go another half of a value. What if we let K equal to 1? Well, you know the game. Here's D of S plus K times N of S. And this hasn't changed. This is S squared plus 6S plus 5, but now we have plus S plus 10 equaling 0. Or now we have S squared plus 7S plus 15 is equal to 0. Now, do we have any algebra aces? Let's just plug it into the quadratic formula and see what we get. And we actually get complex roots. Here we end up with S is equal to -3.5 plus and minus J 1.658. Meaning if we looked at this, maybe you had this factored as S plus 3.5 squared plus something And 3.5 squared is what? No, it's 3 squared is 9, so it's more than 9, isn't it? Then we have 0.5 squared. That's not very big, but then we have 2 times 0.5 times 3. So plus 3, right? So we're maybe a little bit above 3. On to 9, so we're like 12. So this is now, well, you know what it is because I gave you the answer. That's what we have, right? If we completed the square. And now we have roots at minus 3.5 plus and minus j 1.658. Are we doing, now what happens? I don't know if I have the right tick marks. But now where are we? With our triangles, with our closed loop poles. These are our open loop poles. Where are our closed loop poles? They're right there. I just wrote them down. Minus 3.5, right? Plus and minus j 1.6. So now I'm here and about right there. Now those poles, this guy has gone here, and he went from 2.5, and now he's gone up here, and this guy is doing something like this. They actually come together and they meet. They don't like to spend a lot of time together if you're adjusting the K and they go off the real axis. But that shaded line of yellow is actually our root locus. As we're cranking up the gain K, K moved from 1/2 to 1. We moved from 2.5 and 4 to this now imaginary or complex pair of poles. Is that a little bit better than before as far as settling time? What's our dominant pole now? They're now at 3.5, aren't they? Our sigma is 3.5, which is better than 2.5. So it is better, isn't it? So now our settling time is getting smaller. Maybe it's not quite at the value of 4 that we want. Oh, but let's now just keep going. This was giving us something pretty close. What if we now just double it again and say k is equal to 2? Now we have s plus 1, s plus 5, plus 2 times s plus 10. Let me just give you the answer. This is now s squared plus 8s plus 5 plus 20, 25. So that this is now s equal minus 4 plus and minus j 3. They're moving further into the left half plane, aren't they? Meaning we started here and here. Now we have progressed to there and there. Now we are on that minus 4 line, vertical line, aren't we? With a gain of 2. Do we have any overshoot in our response? Getting ready for the exam. Very much overshoot. Now look at figure 5.8. 5.8, do you remember the angle or the zeta value for a 5% overshoot? Zeta of 0.7, right? What's the inverse cosine of 0.7? 45. Is this angle bigger or smaller than 45? So is our overshoot bigger or less than 5%? Up or down, thumbs? Is our overshoot more or less than 5%? Less is down with the thumb, more is up. What are your thumbs? More overshoot or less overshoot? I see quite a few down thumbs, and I hope nobody walks into the room. They think you're evaluating my lecture, right? But that's the correct direction. You're going to get less than 5% overshoot with these poles, which may be okay. That's pretty good, isn't it? We are going to figure out how to sketch this root locus. It's actually going to be something sort of neat. The eventual root locus, if we now had a pole there and a pole there and we had our 0 there, our root locus, this guy's going to go that way, this guy's going to go this way. We've learned that they meet, then they start going this way, and they've moved a little to the left. That 0 is actually going to be like the center of a circle. One will go back to there, and one will march off to infinity as we crank up the gain k. That's a terrible sketch, but it's sort of close. It gives you the idea. That's what would happen as we adjusted k from 0 to infinity in this particular problem. We'll pick up with figuring out how to make that happen more effectively as we move on. But the next time we meet is exam number 2. Please be ready.